know both the fine structure and the field, this speaking is much, much smaller than the initial without activation. That is the first issue. And then we consider the two cases. These two, which one is dominated? So that is second case that we are going to look this PZ, HZ, this contribution and the spin orbital coupling due to this spin and electron move around the orbital, that coupling. So look this ratio, it is equal to, just remind you, is WL, sorry, spin coupling is kind of a new B field, right? It is field Z component, right? 2S spin divided by this one is WLS. This is spin orbital. So that is, I want to look these numbers, right? The ratio of this. Okay, here there's an H. There's an H bar here. H bar down here. So we have, for example, the number. So let me consider the number 3 strong field, right? So that is a strong field, Z impact. We discussed last time. That is when the B, if this ratio is much, much larger than 1, right? So B much, much larger than the WS bar over A. And in this case, we already have the result. In this case, if you remember the Hamiltonian, we can ignore this term. So the Hamiltonian is roughly equal to this. And then here is the joint eigenstates. For good quantum numbers is those N, L, S, N, L, and S, right? No total angular momentum because it's only from the L and LZ and SZ. And from there, we have the correct energy due to this magnetic field that is remind me, then we are going to start from, okay, you can, this is your homework. And do you have the homework 5 from online or you want to? You got it? Okay. So I have a print also. Thank you. All right, so the energy here. This energy, that is, zero, no perturbation plus perturbation term is this one is E the H bar over 2 m. Okay, just I already use mu b, right? So I just use mu. Is mu b m l plus 2 m s. I think we stop here, right? Last time? Okay. Yeah, so now you can see here what is the, when we switch on Mach field, so this is additional term, right? Split the energy level, and you can see the energy level between, the space between two nearby energy level is different from here, right? So that is delta E. That is the difference in LS and L and S. Since the first term independent of LS and MLS, that's only N. So the difference is come from here, right? Is from this term and from here, this term. And this one you will see that is for the difference of okay. B delta ML plus delta 2 MS. So delta ML is either 0 or 1, right? Because the neighbor. The M depend on the L. If L is 0, M is always 0. If L is larger than 0, and the difference between M is always increased by 1 unit, right? So that is difference. And here, this difference is delta MS is 1, right? Plus minus, plus half minus half. So that is the given information. Okay, and this time spectra we know as this is known as the name, the pension, pension bake shift. So that is experiment found is a spectrum shift, and this type shift, if the field is stronger enough to compare with the spin outflow coupling, then you will see this kind of shift. All right. So that is the strong. Now for the weak, there's more information. The weak, a little complicated, is because we have considered the fine structure, right? Not which also for weak field. Okay, that case is B is much smaller than this term. But we have considered this one because since we look this the contribution or effect due to the field. So even though this term is smaller than this one, but we consider this one as a perturbation, right? So in this case, okay, then you will see this is the Hamiltonian is H naught plus fine structure plus. So this all should be considered. But here, since this is a weak, so now this one, if you consider like H naught, right? Right. So now let's consider this as a kind of perturbation, and this one is because this one is smaller than this one, right? So this is dominant, and this is a perturbation. Then we are going to find the contribution from here. So first, we want to find the joint eigenstates. So if there's a joint eigenstate, then we just do this sandwich to find this contribution, right? So joint eigenstates. Okay. To find the joint eigenstate, we need to rewrite this one, and you can see. Okay. Now let me try to rewrite here. H naught is fine. And the fine structure you already know, that is total angular momentum and J squared, L squared, S squared, and JZ, right? So that is. So now this one, okay, here, this term, right? So now I'm going to rewrite this one is this. Q, P, B, or H bar. Now here, this is LZ plus 2 SZ. So LZ plus S is GZ, right? So that is G, Z plus SZ. I can rewrite this way. So now you can see this term commute with those, right? The only difference is here. But at least the good, as a good numbers, what is quantum numbers we can use, which means good means those correspond to those joint eigenstates can represent those. So that is N and L, S, G, and L, G, right? Those. So the joint eigenstates, I mean, in that joint eigenstates is those, not this one. But we are going to deal with this as a perturbation, right? So joint eigenstates is not like this, but here. N, L, S, G, and G. Okay, so now what we need to do is we are going to apply the first, let's consider just up to the first order perturbation. Energy or correction. Let's just correct to the first order. Now, let me first write down and then I'm going to explain. So first order, remember we have the energy correction. Let me use P. Sorry. I treat this one as a P, right? HP. So now HP is Z. It comes from this Zeeman effect, right? So now, how much is B. Remember the first order perturbation that will go to the final exam. This is the inner product of from this zeroth order states, right? So that is N, L, S, J, M, J, and N, L, S, J, M, J. But you see, this one is non-degenerate. Remember, why we use in this case we use non-degenerate, because you can see here I already deal with this as start from zeroth order. So here, this one we already know this energy gave us depend on those quantum numbers, right? So now this one only depend on n. So that is n degenerate. So in this case, we use this one as a non-degenerate perturbation expression for the first order correction. And now you will see it works, right? So now let's look this one. By definition here, right? So then I'm going to apply this term here, this one, right? So that is, let's take it outside is constant. And inside is N, L, S, J, M, J. And here, JZ, right? J, N, L, S, J, M, J, JZ, and then plus SZ. So we have two terms, because here, each one we have two, right? But the first term is very simple, because this is the eigenstates of the JZ. We can easily get this one. Now the difficulty, or we are going to focus on this one, because SZ, it is not the eigenstate of SZ, right? So how to do this? That is next step we are going to apply so-called one of the theorem, which we did not have time to cover in chapter 7. So now, let's for this one. We are going to apply so-called this Wigner and Carr theorem. This theorem is for the products, the dot product or scalar product. Product of any vector operator with the angular moment, total angular moment. So A is arbitrary. So for this case, how to apply this means if we want to calculate average in any state here of this vector, in this case it's a component. Okay, G. So that is a Q. It is components, right? First here, since it's components, so vector. That is for components of this A vector operator. One of component is expectation value, so equal to the expectation value of this inner product or the scalar product. So that's what we use. A in this state and divided by the J square. And this is if this is eigenstate of J square, very easily you can obtain. And multiply JZ. JQ.
What is the Q?
Q, yeah, I'm going to write it Q. So Q is component is X, Y, or Z. So here, whatever the components of the operator A, expectation value is always we can obtain by the inner product of this the total angular momentum is this vector operator and divided by this J square average, multiply the J components. So we apply this. Now here you can see this is SZ, right? So that means A in this case is S. So now we want to obtain N, L, S, J, and J, S, Z. N, L, S, J, and J. So equal to N, L, S, J, and J. N, L, S, J, and J. Divided by N, L, S, J, and J. J square. N, L, S, J, and J. And don't have space here, multiply N, L, S, G, M, G, G, Z, N, L, S, G, M, G, right? So then you can see this we can do. This denominator, now we're going to deal with this one. And this one we're familiar in chapter 7, right? Addition to angular momentum. We can do that so now let's work on this one because others are safe. Here, inner product between spin, total angular moment spin is, because total angular moment is orbital plus the spin, right? So that's this. Then we have L. This is some of the scheme that if you can apply later. When we do is like this, you just consider, try to, like this, we combine together, right? So now you can come to here. And this one, this is the inner product with, that is half of L, yeah, half of a total, right? G squared minus L squared minus S squared and plus S squared, right? Because this is a G squared equal to L plus S squared. So that is L squared plus S squared plus 2 of L inner product with S. Remember this. Now, so, okay, so now I'm going to, so now here G squared minus L squared. Here my half S and plus, so that is plus. Then you can see those are the operator and this eigenstates of this operator. So very easily become, so okay, now we can write down here this N, L, S, G, and G, S, Z. That is very easily we can obtain, which is equal to, so that one is half, right? That is half. Can I immediately write down the final? Because this is a half H bar square, G plus 1 minus L plus 1 plus S plus 1, right? And denominator is H bar square, G plus 1. Do not forget, we have this one, right? So this is a mg H bar, right? Here. So now this is not denominator, so right? So very easy. I mean, in this case, very complete. So now we are going to put this result to here and combine this. So finally, we have this correction, the energy that from this Zeeman effect, and let's see. Some of the Newton physics will come out. Let's see here. So now. Add those terms together. So the EZ1, which is mu B over H bar. And now here, the first term, this is mg H bar, right? Actually, let me write down mg H bar, first term. Second one is that one. So we have H bar already cancelled, right? So this one. So we have a half G plus 1, and the numerator G plus 1, minus L plus 1, and plus S plus 1. Now we have mg H bar, right? So H bar also cancel again, and I take mg outside. So here I have, now I'm going to write it this way. Mu B I keep here, right? I'm going to introduce another number Gj, which is a Landé or factor here, and mg. And we are going to discuss this one. So now if you look this one, if you remember, so this term contribute from where? From this spin dipole moment interact with the Montfield, or Montfield try to align this one to the same direction, right? So now I have this, so speed corresponds to a kind of a dipole moment. Now, now this is total, because this is mj, right? So that should be total. So now I introduce a new magnetic dipole moment, mu j, which is minus mu b, g, and j. Just similar as we defined for the spin, mu s, right? That is negative mu b and gs, and then s, right? And orbital mu l is minus, and mu b is because electrons negative. So mu b, and then that factor is 1, so that's L, right? So we are going to discuss. So now this is introduced, we call magnetic dipole moment. Total speed. Total, sorry. Total angular momentum, which is G, right? All right, so now you see we introduce something new. Two new factor. One is Gj, another is mu j. So now we are going to discuss the details of that information they give us, right? First, let me first give the definition. This Gg. So here, Gg is this term, right? Is I take so that is the 1 plus, factor 1, right? 1 plus. This is what, right? Plus this term. So 2G plus 1, G plus 1 minus L plus 1 plus S plus 1. We code is non-D factor, or they call it general magnetic ratio. Ratio which okay. So now we are going to discuss. There are several issues when we introduce Mach field if the Mach field is weak. So we will find first, let's look this one. For the case if the atom, this is a consider hydrogen atom, right? So hydrogen atom has angular momentum, that's angular maybe 0, 1, depend on n, how much. So in case of L equal to 0, no orbital angular momentum, then how about the Gj? Let's look. This term 0. That means G equal to S, right? Since G equal to L plus minus, L plus S, between the L minus S and the L plus max, right? S, right? So then L equal to 0 is this one. Therefore, you can see this is G plus 1, and S is also G. So they cancel. So here, that is 1, right? This term and this term. Okay, so now that is, remember we say GS. So Y, the spin, if you remember, it's mu S. If you remember, it's minus mu B, 2, factor 2, right? I think I need here. Okay, yes, I introduced this new. This is we have H bar. So here we have H bar, so we have nothing. So that is spin. Magnetic dipole moment, right? We already know before. So then now we know that is come from general to the limit, to the case of spin only. Now second, if a spin is 0, So this means G is equal to L, right? Then you see here, this term is 0. This is cancelled. So that is equal to 1, right? Then the Gj equal to 1, so that is Gl. That is why we have this orbital dipole moment is only this one. That is because. That is another limit. Then now we consider what is general. So for any arbitrary L, any Ls, right? So that is any states. Okay, now we are going to see. So for this case, we know the G has two values, right? G equal to L plus half or L minus half. There are two values, right? Because G is maximum value is L plus S and the minimum value is L minus S. So for G equal to, let me see this one, okay, L plus half. And you just substitute this G in this G value into here. So that details at the same time I will not do. And you will see more easily it is 2L plus 2 over 2L plus 1. We have this formula. So that means when you find this G, there are two values, correspond to G equal to L plus half. That is this one. And for G equal to L minus half, here the reason we have this is because S is half, right? So since this is for any we cannot do this, right? So here, this value is 3/4, 3/4, that is fixed. And then you just substitute this one, you will see finally got this. Then for this one, Gj is 2L plus 1. So you can see it depends on this G value. We have two values. That is correspond to this Lagrange factor. Okay, that is a discussion for this. Then I think I already introduced that, but now let's discuss this number 4. Let's look at this, the behavior of, I think, sorry, yeah. That's okay. Okay. Behavior of the total angular momentum. So this one, let's see here. I think I already write down some here, right? Mu S, mu L, because the mu G which we introduced is mu G is minus mu B over H bar. G now let's use capital G now. Since this G, since I don't want to make so still use this one and the G, right? Okay, but this G, if you can see, if we extend to the details about the G, so G is L plus S, right? And because here, so that is not equal to the mu L plus mu S. Since here, you see mu S, this number should be factor 2. So this Gj is arbitrary. Maybe which one? Maybe, so that means Gj multiply this one, it will not give this one. That makes sense? And then the Gj multiply L, if you're not if the Gj is not equal to 1, it is not this one. So what does means? If you have this angular momentum total J, right? This is the S, this is L, simple addition. But the angular moment, the dipole moment L and S, mu S, their addition is not equal to the mu G. Here, if you, this is not, mu G does not simply addition of the two. That is because it's the function factor here. So that is to keep in mind. Or in other words, this one, this color, we immediately know the direction of this dipole moment mu S since that the opposite direction of spin, and this opposite direction of, okay, that's it, right, this one. But it will not, so this one is followed J, but it is not simple addition of these two. In simple addition, these two is sum of value, but that is this one. This only follow the J direction, but it is not the simple addition of these two. Does that make sense? Okay. All right. So that is the feature or behavior of this mu J. And now let's go back to when we have this energy is there, right? So let's see this number 4, number 5. Let's see the space between the nearby the energy level when we switch on among field. So that is delta E. Delta E is, you see the delta E is come from here. Okay, let me give you the total. Total. So now the total energy of the hydrogen atom, then we consider L, S, J, and J is first E. Zeroth order is only the n-dependent and plus the fine structure. And we know fine structure depends on those quantum number n plus Ez, right? And that is, if you remember this one, let's use E naught, still use E naught since we know that number. And plus fine structure is, remember the alpha, the fine constant, right? Alpha squared. So that is the order of this, multiply E naught and divided by 4n squared, 4m over G plus half minus 3. And then now this is contribution from the Ez, which is the mu B, B right? So the difference from here, right? For giving all the other Gn values, those are this the energy spectrum split is in terms of by this one. Therefore, this energy difference is a difference. This one that is mu B, B, G, right? Because delta mg, if 0 is not split, right? Just use the absolute value. So we found this, and now you can see this one depends on two values. So we have delta E1 and delta E2, right? Delta E1 is mu B B. Let's select one of them. For example, consider the first one is due to this J equal to L plus 1. So that is 2L plus 2 over 2L plus 1 for J equal to L plus half. And another case is mu B, B, 2L, 2L plus 1. That is for J equal to L minus half. So you imagine that this energy is split into two groups. One group has the space between the nearby energy level is by delta E, another is by delta E2, delta E1, delta E2. Okay. One of the examples, you may just, as I said, maybe not have a homework, right? So I want you to practice. Give you this and give you n, you're going to find how many split. For giving you n, how many g, it depends on L, right? So giving n, you have L 0, 1, 2, until n minus 1. Then for giving L, you have a g value. For giving g, you have many this. So you see the split is several subsplit, right? So that ask you to calculate this one, I think you can do, right? That this is a picture, one example for let me see, for n equal to. I think for giving of n and giving L, so you can see without field is 1, and with the defined structure split in 2, and then with the Zeeman effect split log. But there are two groups. One group is for L plus half, and another group is L minus half. Right, so that is the so-called, this one we call norm, here, right? Anomalous. Normal. Here's Zeeman effect. That means if you want to see this spectrum, you will see the two group of spaces, two different space. Then you know, okay, that is the case. The field is weak. Then due to this contribution from this fine structure and this Zeeman effect. All right. A little speed up, and I will give you my notes. So the intermediate lot of some of step I skip, right? I will post on the Blackboard so you know how to derive, for example, from here, how to immediately got here. If you do yourself, that'd be nice. If not, you can see my notes. So this is a perturbation. That means if we remember what is the condition for perturbation. Just remind you. Condition for perturbation if we know H not exactly, right? So perturbation, just remember for perturbation, the condition here. H equal to, if we can write down the Hamiltonian into two parts, and here, this, we have an exact solution. If not, solution. And then the second perturbation much, much smaller than this one, right? But most case, it doesn't work. Exactly in this case, we have a hydrogen atom. Yes, that we can solve exactly. Even the helium atoms, there are only 2 electrons, but with the nuclear, it is also difficult. Of course, now I know do you know Dr. Morrison, John Morrison? He retired. He works on this helium for a long time, and he solved that he can get this analytical solution. But that is very hard and difficult. So that means this is the most case. No, as it is, no such, if there is no such exact solution, what happens? What should we do? That is the most case. That is the most case. For example, in nature practical, we consider molecule, not too much hydrogen molecule, 2 hydrogen atoms. You cannot get the exact solution, so we cannot apply. Then we have to go to variational method. That is, variational principle is more practical. So that we are going to introduce this one, variational principle. So what is variational principle? Is if you not start, of course later you will see this also we need to solve the Shelby equation, but it's not from this idea, it's from here. Okay. Suppose the basic idea is like this. If we know, suppose we know the wave function, and you will say where we come from, the wave function. Yes, suppose we know. Then the expectation value of the energy of system, energy is expectation value of, we just do the integral, right? Suppose we have, this may not normalize, so we need to normalize in denominator. So that is expectation value, right? Now, if we are interested in the ground state, so if the states is ground state. Let's use okay. Then we know this expectation value is ground state, right? Ground state energy. Then similarly, if it is a first excited state, if we know it is exactly, then we know the expectation value is less than the first excited energy. So the Hamiltonian here is any not this the unperturbated. There's no perturbated and non-perturbated. Just total Hamiltonian. And same thing for others. Okay. So now this is if we know. The question is, as we see, we cannot have the exact solution we do not know. Then how to find this the energy ground state energy? Right, so but we do not know. States, ground states, etc. So that means we cannot get. Okay. Now, but if we give since we do not know. Then what we do, right? Then we know any function in Hilbert space, we can explain in terms of the basics, right? Then any, just according to the superposition principle. Superposition principle. Any linear combination, right, principle. So any states can be expanded in the linear combination non-use index NCN. Here, these states, this is just I say basics. If I say vector, because now the language I think you understand, right? The basic vector means that the vector, they are independent and form the space of the n-dimensional space, a Hilbert space. So that any function can be expanded in terms of those. So here, this one may be eigenstates, may not, may any others. But if they can they obey this condition, that's all. Okay, so that means release the construct condition, right? So now let's see. And how to do that, that is later we're going to give you an idea how to construct, so-called construct the trial function. But let's suppose we have this. Then now, okay. So in case, right, suppose if it is the eigenstate, suppose, right, because we do not know, but let's see what happens if we do this. Is a eigenstate of H. That means H, apply this state, give us En. That is, of course, we say that we cannot find it. It is hard, but suppose it is. Then we know the energy is the expectation value of Hamiltonian sandwich between the states. So if we substitute this one into here, you will see that is summation. We have two summation N, M, C, M. Coefficient, right? That is coefficient M. Then this is phi N, H, psi M. And denominator is also the two summation Cn, Cm, N, N. So we know the denominator, this one is normalized. So we have only one summation Cn. This one, let me just write again. Cn, Cm. Because it's eigenstates, so that is En. Delta n m, right? Because eigenstates then become En multiplied psi m cat, so bra right n, right? So that is this one. Then finally, also we have one summation reduced. So now let's look at this result. What is this? Okay, so let me, if you agree. This value must be or equal to the ground state energy or must be larger, because depend on this coefficient, right? This probability to find energy in a different level. If the probability to find, that means the coefficient gives the probability to find this energy level at 0, ground state is 1, the other must be 0 because probability. Then that is equal. Otherwise, always larger than this one, right? That makes sense? So that means if we select, even though it is the eigenstates used as a basis, but for any function, we do the expectation value, the result is always above the ground state. Then, okay, so now, because this is we select after, but now we want to see. We are going to try to find the minimum, right? Because minimum is E naught, right? Is a ground. So let's try to adjust or optimize this psi such that the expectation value will give us reach to this one. So that means we are going to minimize energy is a function, because this is a function of the energy. Expectation value is a function of the psi which we select. Right? You can select different, that means different type of wave function, but because this is a different coefficient. So you have different wave function, you will have different values, but I'm going to optimize the wave function such that the expectation value is close to this one, right? So that means this one means try to minimize, let's use the notation here, minimize the energy, minimize or optimize, try to adjust this one such a minimize energy that equal to 0. Then we have, so we have, now we have the expectation value here. Suppose this one is, this gives us a new state. I'm going to use psi star. That means we find that one. We do not know, but let's try to optimize. You may say how to do that. Later we are going to do. So suppose we find one such that the change is 0, that means minimize the smallest value, then the expectation value for this will give us very close to the ground state. Suppose we can obtain, right? So that is not equal, so very close to this. Or that's still upper bound, but very close. Above a little bit, not too much. That is, if you select good, for example, we can find this real exact ground state that is equal, right? Otherwise, you will select larger, so that is always upper bound. So this approximation, we call this is the variation principle. The basic idea. Okay, so now we focus on how to select the wave function such that then we can obtain this expectation value. So that means key is try to find or optimize this one, and then we are going to do this integral expectation value so we can find this ground state. And that ground state energy, then this one is close to ground state. That is the idea. Okay, so now the question, how to do that, right? How to do this? Okay, so how to do this is that we are going to construct a trail function, trail wave function. Now we use psi trail. Okay, then we are going to try to, that is the how to do that. Try to find this such that the energy under this expectation value under this trail function. Okay, I think inside this. subscript is no space, so I'm going to use here. So that is a trail. If the trail function is not normalized, you need to normalize. First, do this. And then second one, just optimize. Try to find the minimum. Then try to optimize the trail function such that we get this. So finally, we will have this the trail function, which particular is give us energy and this optimized trail function, which is close to the ground states, and the states, the trail function is close to the ground states. So how to find ground states and ground state energy, this is how to do. So the key is here, right? How to construct this one, that is the key. Then now let's do next step. How to construct. This is a challenge here. So yes, no fundamental or unique way. We have to use our physical intuition, our knowledge about this behavior of the states, and introduce some physical properties as adjust the parameters to get this. So that is how to do that. Let's use the physical intuition. And these educated, since we are already educated, right? Educated guess. And how to do that, we are going to go through one example, see how we do that. And also take some parameter which is adjustable, which control those behavior in taking into account all the physical properties. If we consider ground state, right? So if you consider first excited, you will go to excited, the ground state. Also symmetry, for example, anti-symmetric behavior, or these wave functions we have a spherical symmetry or one-dimensional, even well symmetry, whatever. So those information is also very important to help us to construct this trail function. Symmetries, number of nodes, right? The wave function have nodes oscillate, so the number of nodes. If this ground state depend on there's no nodes, and behavior of infinite, like asymptotic behavior of infinity, etc. So those are all the information to help us to construct this trail function. Once we have this, then we can go. So now let's see examples. Suppose we have this trail function, right? Can be parameters of all the properties we do not know, but we can optimize the parameters of alpha 1, alpha 2. All these are parameters which we can adjust, which characterize the physical properties. Or, okay, that is the, you have use those. Another way is we are going to use the superposition principle, and those are we call the variational ansatz, which are used more popular in the computational simulation. Right? So that is this one. Or the trail function is this way, or the linear combination. Now I'm going to use I, not N. N usually we say this eigenstates, right? Now I, I. So here it is a basis, variational basis set, and this one, the coefficient we call the variational ansatz. Here, even though this summation may not include the whole, if the n-dimensional space or infinite dimensional space, that is infinite. That is, but in most cases we just truncate to certain level. That's enough. That is, and then the goal is try to adjust this one to make this more close to the ground state. So this is a more popular way or popular method in this computational physics or chemistry. Physics or simulation. So, because of time limit, so I may select one, this one and this one. See. Okay, once we have that, right? So that is how to construct the trail function, either this way or this way. Then we can just calculate. So now, let's see. Now, how to. Okay. So next steps, right? So now, once we have. Just how to find E naught and say not close, so that let's say the first step you do this expectation value. We have a trail function. So now the trail function is, suppose let's use this one, right? And later I'm going to use it alpha 1, alpha 2, all these parameter edge and these states. So that is after the expectation after interval is a function of those parameters, right? So finally, is B equal to a function of alpha 1, alpha 2. Then now after this, so the first step, right? How to find the first step, second one. We are going to optimize that, apply this variation principle. So now I'm going to optimize the energy with respect to the parameter. Let me try to find the parameter alpha I equal to 0 for I from 1 to. So you have a series of equations. Each one you are going to optimize the one of the parameters to make this 0, and then you can determine which parameter, the alpha 1 equal to how much. That will give us the ground state. Then you are going to find a series of alpha, optimized alpha, so they have energy as a function of alpha I, which is close to energy here. Then this the trail function. Looks very simple. So the difficulty is here. First, how to construct this one, and then do this one. Of course, is also the integral. It's also, since Hamiltonian is complicated, right? So this the integral is also complicated or takes time. Use our math knowledge. Now this is for ground state. We can also extend to how to find E1, the first excited states. We do the same thing. So now let's try to again find or construct same thing. Construct for the same thing, but construct the trail states. Now I'm going to use 1 here. Different trail states. And then you calculate this one, and this you find this trail states for the new one. Then you do the number 3, you optimize the, now I'm going to use E1, since I want to say this energy, I hope to go to this first statistics with optimize this one. If I use, I did some index too much. Just do this equal to 0. Then from this one, of course, this function is a different type of or group of parameters. Then you have this energy. Your obtained energy is minimized is be larger or equal to E1. Then this gives us minimized energy, right? Too many notations. So let's remove this one. This energy is just correspond to the expectation value of the say 1 trail function. So then we minimize this one correspond to our upper limit of E1. Then this the trail function correspond to that one should be expectation value of this first state. However, one more thing. We need the orthogonal. So you need double check. Once you select this one, of course, first if we can have more educated idea or knowledge and to construct one, the first one in particular use the knowledge about the number of nodes. They may automatically orthogonal, but if not, after you do this, you have to double check this. If not, you have to adjust again, right? And similarly for the second order, excited states, so similarly. Now, let us, the textbook has a lot of examples, for example, in this one dimension or hygiene item. Let me go to the most important application or successful application for this variational principle for the healing. So, let's see how successful the variational principle. See how can we construct this trail function, how to calculate this one, and how to optimize. Find the ground state energy of healing item. So now let's consider first healing, right? Healing we have, I'm going to use Z, but Z equal to 2, right? Plus here, the nuclear. And then we have a 2 electron here. This one, so I'm going to say this R1, this R2. And this difference is R1, so R2 minus R1, whatever, right? Okay, if R1, so that is whatever the direction, but that is picture. So you can see the difficulty is here, we have additional. If the only one is a hygiene or hygiene-like item, so we can solve very easily. But we have additional the difficulty compound interaction between electron and electron. That's the interaction. So now let's see. Okay. So first, Hamiltonian. Hamiltonian, we know kinetic energy is each individual electron, right? We just consider the set. This is the interaction between, due to the Coulomb potential for the system, consider only 2 electrons, not the nuclear. Just nucleus interaction contribution, right? Nuclear. So let's do this way. And same thing on the first electron, second electron, kinetic energy. Then the Coulomb potential energy is each individual electron interact with the nuclear, which is attracted. So the negative, which is Z E square over R1 plus Z E square over R2, right? That is the interaction between the electron and the nuclear. But we also have additional interaction, is a repulsive interaction between electron and electron. So that is plus E square over R. That's just because it's a distance, right? So R1 minus R2. Okay, that is make it difficult. Why? You see, this is a two-center integral. When you do the integral, or we are going to do the integral, right? So you can see here that you cannot separate integral only R1 or only R2 individually. Those are individual, right? So that is difficulty, and let's see how to deal with. Why these helium atoms? The exact solution is also very challenging. So now, how to find the ground state energy of this? They call the ground. Okay. So now let's first analyze it like this. The first one, experiment, already experiment measurement. Is E ground. We are going to use this one to judge or how the either perturbation or variation method, how good it is, right? So let's use this value. 78.975 electron volt. So now we're going to consider here. Second one, let's if we ignore, since we know that is ignore, right? Ignore this. Okay, I'm going to use this this term EE. EE is the electron interaction. Let's first ignore this term. So the Hamiltonian is only the non-interact 2 electron, right? Combined. So that's I just easily use H1 plus H2, and each one Hi is I equal to 102 is the kinetic energy part and plus potential, right? So we can separate. Either separate, then so we can easily solve this. So now here, this is each one like a hydrogen lag. Lag item, right? Single, the only thing, oh sorry, this is Z. The only difference here is Z, right? If a hydrogen Z equal to 1, here Z equal to 2. So if like hydrogen lag items, so we immediately have the solution, chapter 6. Now for each individual, E and I, the ice particle, we have ice electron, right? E and I is Z square E naught and N I square, right? And then the ground states psi N I L I. If we do not consider spin, let's just consider this ignore spin. So R I. For ice particle, the ground the wave function is radial part N I L I R I, and multiply the angular part with the spherical harmonic spherical function L I M I sigma I from 1 2. Then, if let's say if we ignore so the ground state or the let's say the total, right? So now the total is N1 and 2 is E and 1 plus E and 2, right? total energy of this two electron system is just each individual electron energy put together, and that is here we have this formula here with this Z square E naught and 1 over N1 square plus 1 over N2 square, right? And states. So the states for two electron, just make notation make it simple. So now this is a product of the first one, N1, L1, M1, R1. And since no interaction is direct product, right? The wave function is just the product of these two. And each individual pair. Okay. Suppose then what is the ground state? In this case, ground is when N1, N2 equal to 1, right? So that is Z square E naught 1 over 1 plus 1 over 1. That is 2 Z square E naught. How much? Since we know E naught is minus 13, right? Z is 2, so that is 8, right? 8 E naught. And that is minus 108 electron. You see the compare this difference? Big, right? So you can see this difference of the E ground calculate minus the experiment E ground measurement. The ratio divided by experiment E ground value. The deviation of the calculate if we ignore this electron-electron interaction. How accurate? We will see the accuracy is 108.8 minus 78.975 over 78.975 multiply 100%, and that is big, 37.7%. So that means it's too big, right? That means conclusion is this term cannot be ignored. That is in another way to prove or show how important this interaction. So then we have to use the variational principle since this start from the beginning, then we can. Okay, now number 2, 3. So we are going to take into account the VE electron-electron interaction. Okay, so in this case, and apply variational principle. Okay. So how to now the question is how to construct, right? How to construct. This one we need adjust this Hamiltonian in a way such that because this term is big, right? So we are going to make this rearrange this or manipulate Hamiltonian such that we want to find another term which can use the variational principle is small. So I think let me just very quick. Let's. Just introduce the idea, and next Wednesday we are going to consider. So here you can consider. This is a plus, right? So we have an electron here, and you have an electron here. Then you see this electron move as a circle. So we have a screening effect, means the interaction, actually the interaction of between this one and this one is weaker than without this one. Because this one move around very quickly, it's a cloud. The cloud is try to screen the strings between this one, right? So that is the screening effect. That is the education or physical iteration we are going to consider. Then we have this effect, so we are going to consider how to construct this by taking into account this effect. That means this one, if this is 2, actually the interaction between this electron and the nucleus is less than 2. So that means this one, the z should be as a parameter, which z prime is smaller than z. That is the idea. Because this is come from here, right? Come from this term. And this term is that we have the 2 electrons move around, and then this another electron, when they consider the interaction between this one and this one, another electron move very quickly, so that make like repulsive. We'll try to make weaken this interaction between this. So that means if we use those, here the z is be smaller than this value, right? Okay. So we have remaining 2 class, Wednesday and next Monday. Next Monday, I will give you this take-home exam, and then we fix, right? That is May 1st, right? You're okay, right? May 1st.
Okay.
The in-class exam. It's from 1. Okay, yeah, from 1. All right, I'm going to remind again. The homework, if you can finish by Wednesday, I would like to have it and great for you. If not, Monday is also fine. And as I said, I do not have time to assign homework for this part, variational. And also, I think we have time to cover the.
I think some of the questions that you had on there were related to what we covered today.
Which question?
33.
Oh, okay. 933 is perturbation. Yeah. You mean the sum of like the I don't remember the I assigned the homework is one of these like the fine structure. You mean 9.3 is 0.3 is 1 dimension, right? You just
yeah.
talk. So another one.
933.
930. 933 I didn't assign as it's 939.
939.
Yeah, 939. Yes, that's the integral here. Okay, yeah, if you can practice, that'd be nice.
Can I ask you a question about 939?
Okay, let's see, 939. 939.
Are we given the integrals as a hint because we need to normalize the wave function?
This one, this is relativistic contribution, right?
Right.
Yeah, this one, in the class, I already show how to get this P4, right? You just square out that, and then you do the integral, because P is second order derivative. And then after duty, you do the integral, so that I give you hint. Some of the integral, this type of integral you may need it, and you just use one.
And that was for the harmonic oscillator.
Because
So,
next Friday, because
I was
next Friday we
saying
take our
for like constructing the wave
final.
function,
Next week.
Okay,
Friday.
yes.
Then we have
for
very
constructing the wave
Yeah,
function,
Yeah, very
Small
strict.
time.
the integral comes
Yeah.
in
So,
whenever we are
the Friday
calculating
and the
the
next Friday.
second order
Oh,
term.
that's my
Okay,
bad.
is it comprehensive?
You mean the second order
Yes.
perturbation?
Really?
Yeah.
What do you mean?
So,
From first
HP.
slide?
Yeah,
yeah,
HP,
so
let's
maybe a good
let's
way to
ask
study
you
for
to
it is
correct
Yeah.
the ground to
look at your midterm.
first order,
So
right?
you got
Right.
one.
Yeah, you
And,
just go for the second order
Yeah,
comes
focus
with,
on the midterm and the homework.
yeah. Also,
I imagine
another
they
one
pull
is
some from the
44.
very recent homework. 'cause that's what you do.
I finished. I don't know.
Yeah, that's what
This last one, it's easy.
spin, and spin orbital, yeah, that
Especially the first question.
SO.
I have all the
It's
lectures.
And use the result, and you can find the spin of the correction to, yeah, that is okay. That is formula. Yeah, and find what is the N have and the L and G values.
I haven't started to prepare my slides.
Okay,
Fair.
does that make sense? Yeah,
I think I need to write some
Okay.
out.
Hey,
Yeah.
Kai, how are you?
Say how are you?
I'm good.
okay, yeah. Almost the same as I described in class.